After 8 episodes of ConQuiz series, I thought that what if I go for a change? So I'm switching over from chemical kinetics to thermodynamics. And once again, I thought that after 8 episodes, if I give a bonus episode, how it would be. So today I am not numbering my session as ConQuiz 9, rather I would like to call it ConQuiz bonus, and this is on concept booster on thermodynamics. And today's session is really very different, very exciting, and it's quite amazing as well, and very applicable, full of utility, because today's title is how thermodynamics can be reduced by 50%, just on focusing on some important concepts, correlation and connectivity among the different concepts and different equations. So it's really sounding very amazing and magical. It really works very magical, but it's not magic really, because the thing behind this magic is simple, pure mathematics. So let us see how we can reduce the load of thermodynamics to its half. Before I go for that, let me just cite a few common problems with students and sometimes with teachers. Right? If you just open a thermodynamics topic in any textbook, physical chemistry textbook, you will see that page after page, it's quite mathematics and mathematical jugglery. Equations, really there are so many equations. So is it that understanding thermodynamics equivalent to a memory game? Though not really, but sometimes we, the teachers, are responsible for growing a tendency in students to avoid or to get afraid of mathematics, right? Very unfortunately it happens with many students, because it simply happens because we cannot correlate the things and we cannot see the connectivity among the different equations and concepts. Particularly if we can find some pattern of that connectivity and correlation, the whole thing is made very easy. So that we will see today. So thermodynamics can be reduced to half of its load. Wow, really? But what it means by 50% reduction of its load? So let me explain. Suppose you are considering the whole equations, a lot of equations, and we just divide into two sets, one set, one half of the thermodynamic equations, and if you get the other equations of the another set parallel to the first one, similar to the first one equations, with one-to-one correspondence, and correspondence with respect to what? To the origin, source, meaning or significance, expressions, derivations, utility, and whatnot. So they are very parallel, and if you get such with a simple minor change based on some pattern that you discover, then actually it is equivalent to say that the other set of that set of equations is magically automatic. So what I demand that if you can understand 50% of thermodynamics, the remaining 50% is magically automatic. So let us see. And it all originates from pressure, volume, harmonic. Pressure, volume. So it reminds me of a film long ago, Albert Pinto का गुस्सा क्यों आता है. So I have borrowed the concept that P, pressure, को गुस्सा क्यों आता है. As you know from Boyle's law very earlier, that pressure and volume are inversely related. That means V decreases as P increases and the vice versa. But that is not the reason for P's being angry. Actually, the reason is like that. Q, heat change, is not a state function, as you know from thermodynamics. But at constant volume, Q at V is equal to delta U, because from first law you see dQ is du plus PdV. If you put V constant, so PdV is 0, so dQ at P is du, and integrate to get Q at V is equal to delta U. But U is a state function, right? So that means under certain condition of V, that is constant V is important, Q behaves like a state function. So as if V is playing a very important role to make Q a state function under his condition. Okay, but no state function, assume that no state function, say X, from either first or second law or thermodynamics as such, no X is there, so that you can say that Q at constant pressure parallel to constant volume, Q at P is equal to that change of that state function X. So in that case, P would have behaved like a state function, that Q, but it doesn't happen. So far we are assuming that there is no such function. Thermodynamics resolves this problem. So how? Let us just play with this equation X new function that I'm in search of for making Q a state function at constant pressure condition. So X is U plus PV, and take the differential, dx is du plus pdv plus vdp, but du plus pdv is from first law, that dq you know, vdp. So now you put condition P constant, so you get dx at P is equal to dq at P plus 0, vdp is 0 at constant pressure. Okay, so now we can say after integrating that Qp is equal to delta x, where x, is it a state function? Yes, the way I have defined x, u, p, b, all the right hand side terms are state functions, so x is also a state function. So the problem is resolved by thermodynamics. We got a new function x. Now we can say Q behaves like a state function at constant pressure too. Okay, actually know that this x is nothing but enthalpy, or we sometimes call heat content. Okay, now why harmony? Mutual coexistence, a clue. If you write down parallelly du and dh, this x is now h, so is dq plus vdp, and du is dq minus pdv from first law. So you see that as if u is replaced by h and p is replaced by v and v is replaced by p. So it's a game of flipping over pv and uh, and of course a minus sign is replaced by a plus sign. So it's a game of flip over, right? And that's the clue. Probably that pattern, that replacement p by v, v by p, or u by h, or h by u, this pattern would survive throughout the thermodynamics. And if it is so, then it's really magical. It would work magically. Let us see how magical it is. So harmonious coexistence, sharing members. So we can think of that P and V, they are mutually coexisting, but in two different islands. So P is say East Bengal and V is Mohun Bagan. And when two new players came into the ground, U and H, U is joining Mohun Bagan, U, and H is joining P, East Bengal. So as we have seen, QV is delta U and QP is delta H. So U and H are evenly distributed among two clubs. Not only that, U and H is the relation. If we just rearrange, then you see that U is replaced by H is replaced by U, P and V by V and P with a minus sign changed by plus one, right? So that is, I think it's very clear that how I am flipping over the variables U and H and P and V and plus and minus. Okay, so let us see how far it goes, this harmony. It continues. How? If you combine first and second law, du is TdS plus PdV. So what we expect from our pattern, that U should be replaced by H and P should be by V and V should be by P, and a plus should be replaced by minus. So what we expect is dH is TdS minus VdP, and really there is a relation dH is TdS minus VdP. We can check it. I have already shown that Q is du plus PdV, so the similar parallel Q is dH minus VdP. So PdV is replaced by minus VdP and du by dH. Okay. Now a very common heat capacitor specific heat, CV. So if CV is there, definitely for East Bengal club some CP would be there. So there is some Cp. And not only that, the expression you look, d del u and at V, it is del H at. So again, the flip over game is running on. Harmony continues, Joule and Joule-Thomson. So if Joule is there for V club, then Joule-Thomson is there for P club. For example, in Joule, it is delta U equals to 0. So similarly, we expect that in Joule-Thomson, it should be what? Yes, you have rightly guessed, delta H should be 0. So delta H should be 0. Not only that, the Joule coefficient and Joule-Thomson coefficient, they are also very similar and parallel with one-to-one correspondence, following the same pattern that we are talking on, del T del V U. So you expect del T del P H. So del T del P H. And not only that, the after derivation, the final expression that you get for Joule's coefficient is minus 1 by Cv and del U del V at P. So you expect minus 1 by Cp, minus 1 by Cp, and del H del P at P, del H del P at P. Okay. So far they are very parallel. If you can remember the first set, you can easily handle the second one, right? Harmony continues, thermodynamic equation of state. So how many equations of state are there? Actually, often people say that there is one equation of state, but actually there are two, and from my PV harmony concept, there should be, because if one equation corresponds to the V club, then the other equation must be there for P club, for his spin off, right? So this is the very common one, that del U del Vt is T del P del T V minus P. Okay, so you don't bother about the other equation, just follow our pattern, PV pattern, that you expect that U should be replaced by H, V by P, and P by V, and this suffix V by P, and P by V. Not only that, this minus to be replaced by plus sign, and here a plus sign is there, it should be replaced by a minus. So let us see, and you check del H del Pt like del U del Vt, and here minus P was there, so plus V is there, and T del P del T V. Now here it's minus T del V del T at P. So P and V are switching over, flipping, and U and H up so far, they are also being members of two different clubs, they are also flipping over. Okay. And for ideal gas, we know that del U del Vt is 0. So similarly, we expect del H del Pt equals to 0. Not only that, we can show that del U del Pt is also 0. But here again, you expect that del H del Vt also 0, right? So far so good. They are exactly parallel, and you will agree with me that from the left hand side equations, you can get easily by the simple trick the right hand side equations, right? Maxwell's relations. So there are 4 Maxwell relations, you know, and I will show that how again they are very parallel. Say for example, PVS is minus PSV. So what we expect from our pattern, that TP at S, so TP at S, and VS at P, VS at P. Not only that, the minus sign is replaced by plus sign. So you can follow the next one also, SBT PTV, and that gives you SPT minus VTP. So you can give a pause for a few seconds, look at carefully whether really my demand is true or not, that harmony is going to be reduced by 50%, and then when you are convinced, you can come back to the video. So let me continue. Isobar and isocore. So I am not going into the details. Vent of isocore is there, so there must be a vent of isobar. If Kc is there on your left, then Kp must be there on your right. PV harmony continues. Helmholtz and Gibbs. So A, Helmholtz functions, U minus ds. So what do you expect on your right? Yes, you have rightly guessed. It should be H minus ds, and that is Gibbs energy. Similarly, the differential form, total differential dA and dG, you can easily check that how this PV and PV harmony is existing. Spontaneity and reversibility or irreversibility condition, in terms of A, there is a relation, but at constant V and P. So you can easily say now that there must be another condition in terms of G, and not only that, at constant P and P. So that is exactly the same, dgpt less than equal to 0. It's most useful equation in thermodynamics. Another spontaneity condition, du SV. So you expect now DHSP, right? The chemical potential we can express by this del A del N. So, and by definition, this is del G del N. Here suffix is Vt and here it is Pt. So PV harmony is still there. Not only that, we can express chemical potential in other form using U, and similarly you can expect using H. So really chemical potential can be expressed either of these four forms, right? Now, as I promised you that it sounds and it works magically, but it's not really magic. Behind all these things is simple pure maths, and we call it transformation, Legendre transformation. So now if you bear with me a few more minutes, you can get this secret disclosed to you, how it all comes. Okay, so are you ready? Thank you. Well, let us suppose that there is a function f, function of x and y, and you can write the total differential df as p dx and q dy. Okay. Now, what you want to get a new function, say capital X, which would be a function of x and q, not y, x and q. So you want to define a new function. Let us play that starting from the original function f, which is given to you. Now f minus q y, because you want to replace y by q. So you take this product of q and y, so q y. Okay, these are called actually this q and y or p and x conjugate variables. Okay, so okay, let us play more. Evaluate dx. So you evaluate dx. Dx is df minus d of qy, but df is p dx plus q dy. So p dx plus q dy written in yellow, and d of qy is of course q dy minus y dq. Okay, so you see that q dy and q dy, they cancel out. So finally you get p dx minus y dq. So now you can say that yes, we have got a new function x, function of x and q. So we have got new function of x and q, and the definition goes like f minus q y, and the total differential is p dx. So p dx is as such there from the original differential of df, but q dy, here the trick, if you see carefully, that q dy just a flip over game is there. Y comes here, q goes there. So q dy becomes y dq, and plus is becoming minus. So q dy becomes y dq. So I repeat that if you don't like x to be any more functions, so you want a function of y, you want a function of x and q, then you first of all you take x to be f minus q into y, and then the differential will come as p dx minus y dq. So it was q dy, it becomes y dq. Okay, just flip over is there. So similarly, the same question you can raise that okay, if I want y but not x, that means if I want a new function of y and p, not y and x but y and p. So what we will do? We will follow the same similar strategy, that I will define a new function, say capital Y, and it will be like f minus px, y px, because you want to eliminate x. So you take the product of p and x, this conjugate variables p and x, And if you evaluate dy, then after cancelling the terms, you will see that dy comes as q dy. That means this part is remaining as such, but p dx, again that switching over is there, that flip over is there. P dx become x dp with a minus sign. So x dp with a minus sign, right? So that is a new function. So we can say that we can define a new function from old function f by simply making f minus px if you don't want x anymore as a function variable, and then the dy becomes the q dy as such, and here a flip over x dp minus x dp. Okay. So let me summarize that x and y, two new functions are defined from f. The total differential is given like this. So in one case I am doing f minus q into y, and other case f is p into x. In first case dx is flip over happens over here, y dq with a minus sign, and in the second case flip over happens here, that is x dp with a minus sign. Okay. Now a question may arise that can you think of yet another transformation that where in the new function say z there would be no x, no y, rather I would like to have z as a function of p and q. Then how I would define my new function z? So I think you can give a wild guess that in one case you have taken minus qy and other case minus px, and in this time you don't want either of them, so you have to define z, a new function, as f minus px minus qy. Yes, if you have guessed like that, you are right. So z is f minus px minus qy. And what would happen to dz? So again we can easily check. You take the differential and you can easily check that after cancellation of the terms you will get minus x dp minus y dp. So the trick is that even if you don't bother about the derivation, the trick is that in the earlier cases, once you have made a flip over here and in other case a flip over here, but now you are probably going to flip over in both the cases. So x dp with a minus sign and y dq with a minus sign. So exactly x dp with a minus sign and y dq with a minus sign. So that is all about the transformation from an old function f, which is a function of x and y, you are going to a function x, y and z, right? Now let us see examples and in real thermodynamic terms. So what you need to start with f, right, and df. So what is your f? Okay, first law, u is my f, and from first law and second law combination, what is du? Tds minus pdv. So it looks like df is pdx plus kdu. Okay. Now what you want initially? Suppose you want to keep s but not v, rather you want p. So you want a function, new function in terms of s and p. So what we will do? Old function minus qy. So that means v and minus p, right? So v and minus p. So u old function minus v into minus p, that is u plus pv, and that actually is enthalpy, heat content. Okay. And dx, as we flip over here, y dq. So similarly you have to flip over in this pdv. So v and d of minus p. So v and d of minus p, and that would give you tds plus pv. Okay. So you get dh directly from the pattern or transformation tds plus vd. Okay. So now you can raise of course the second question, that if I want another one, that means you want to keep v but not s. So what we will do? So similarly what we will do, we will define a new function u old function minus, this time you are handling t and s, this conjugate pair, so t into s. So u minus t into s. Okay. So you just apply the flip over rule, that now this time it would be on tds part. So after flipping over you get s dt with a minus sign, and pdv remain as such. Okay, minus s dt. So dy is minus s dt, and as you know that this y is nothing but Helmholtz energy u minus ts, and that we denote by capital A or sometimes capital F. Okay, so we have got two examples, thermodynamic examples, and why not the third one more example. That means if I want to eliminate both s and v, rather I want a new function in terms of p and p. So obviously now you can guess easily that I have to take a function z, new function z, like f minus both qy and px. So you can get it that u minus v into minus p, this one v into minus p, and minus t into s, this conjugate pair. So product of conjugate pair, two pairs, and that it gives you u plus pv minus ts. But so far we have already seen that u plus pv is h, so this is h minus ts. And as you know, this h minus t is nothing but g. And not only that, the dz differential, you have to flip over both these two. So s dt with a minus sign would be there, and v d of minus p with a minus sign there, that means minus minus plus, so vdp minus sdt. Okay, so if you take dA and dg parallelly, the harmony would be even more clear. The dA and dg, as we have already got, is minus p dv, so here it becomes v dp plus, and minus sdt is common, minus sdt is common. So dA and dg, they go very parallel. Okay, so I think you will be convinced that yes, after today onwards, your thermodynamics load is really 50% reduced. So thanks for watching. Our next video would be coming soon, and that would be on concept booster on thermodynamics. Probably we'll start with rapid fire, then will be short answer type questions, and then some conceptual multiple choice questions, and probably some questions taken from IIT and JAM. So stay with us. Please keep on watching. Do subscribe. Encourage your friends to subscribe, to watch videos, and to learn. Thank you very much. Till then, goodbye.